I'm Andrew Ng, founder of deeplearning.ai, and I'm excited to welcome you to our global deep learning community. I know that many of you are here today because you want to break into AI and build your career. I hope that being part of this community will help you to do so. Our team is working hard to support you and help you learn. It's never been easier than before to break into AI. So if you want to build a career, you can leverage online resources available, including open source code, datasets, papers, and online courses like a deep learning specialization on Coursera. As part of this journey, I hope you get your hands dirty too. Don't be afraid of diving in to build your own project, or go ahead and try to replicate a research paper that you're excited about. One thing that I've seen help a lot of people succeed is if you can build a community or find a community of fellow deep learners you can meet with and study with on a regular basis. In fact, I hope that this Pie&AI meetup that you're at right now will be a good place for you to meet these people. I hope you enjoyed the event today and that you learn a lot both from the talks and from each other. And once again, welcome to the deeplearning.ai community.
We expect to see the importance of deployment of 5G, and new services based on 5G will enable such a complex distributed architecture. But in any case, even if it's not 5G, the need of distributed intelligence and then the application of edge cloud technology is seen as a critical element. But we focus specifically on what artificial intelligence can do in this field. I tried to identify some key features and functions, filtering pre-processing of raw data, innovative algorithm for monitoring in particular, pattern recognition, and data analytics. In the following, I picked some concrete examples with also practical application in which in different projects we have been using methods coming from the artificial intelligence field and applied in the real life of electrical systems. The first one comes from the European project Coordinate. Coordinate is a project that is trying to understand how grid operator can better cooperate. In particular, these two sections of the grid I mentioned before, the one traditionally smart, the transmission, so the high voltage network, and the one that has to become smart, so-called distribution network, so medium and low voltage. A coordination of the operation of these two levels is one of the critical aspects, and traditionally, vice versa, there was very little communication and interchange of data between these two levels. Here, we target a specific problem, which is the creation of flexibility market. Flexibility market is the tool the grid operator has to compensate volatility of energy from renewables by exploiting flexibility at the load side. So traditionally, we were not concerned with what the customers were doing because we could adapt generation. In a new scenario in which generation changes because the wind condition changes, sun condition changes, we need to access the load as flexibility resource to keep the network balanced. That's because in the network, the network is a system that intrinsically has no storage. As much energy as we bring in the network, the same amount we need to take it out of the network in some form. And that's where the problem of coordination of grid operator and the creation of flexibility market is one of the most important part. Here, we look at a specific use case that was done in the project, which deals with the management of the grid in Sweden, in which the grid operator at the lower levels, the grid operator DSO, has to guarantee that he will not overpass some threshold of consumption during the day. Otherwise, we'll have to pay penalty to the other section. But this is hard to manage real time. So the normal approach is to work on prediction. So having the feature of calculating what will be the next situation in the next 24 hours and trying to understand if challenges may arise and in case activate market of flexibility that will provide the solution when needed. That means that the prediction, so on understanding what will be the consumption pattern of energy, so the energy exchange between the high level voltage of the grid and the rest of the grid is a critical variable to take commercial decision. So here, as you see here from the slide, the goal was to predict the need of flexibility 40 hours in advance so that this market could be enabled and the right purchase of flexibility could be done. The point is for the grid operator to avoid penalty because they will consume too much respect of the contractual exchange at the point of delivery. And here we see we have been working together with the grid operator and testing a variety of algorithm of prediction coming from the literature and using available data from the local operator to try to tune these models. What you see here, anytime the red bar is that limit that we should never pass during the day. Otherwise, the operator will be on a penalty situation. And then you can see the real consumption that was registered and how the prediction model are able to match this the reality is as a prediction though in the blue line. So as you can see, the prediction are not too bad. The experience quite somehow in certain element obvious is because here we are working on interface between high voltage and medium voltage. We cluster the behavior of a significant number of people, so statistically it's quite easy to reach a level of prediction that is reliable so that the grid operator can actively have a view of what will happen in the 40 hours following and try to get reasonable results. Problem though is the more we introduce renewables, the more this prediction has to keep renewables into account. And then the volatility and the uncertainty and prediction from the weather part reflect in a volatility and difficulty and prediction on the electrical curve as well. And this is where a lot of the challenges in building algorithm for prediction are appearing. What you see here is that the work was brought all the way to a real platform and implemented. This is the dashboard of used by the grid operator in Sweden to take a decision if in the next 40 hours there is a region of risk. And here you see a case in which was pretty clear from the prediction that was necessary to access flexibility to make sure, that the red line was not overpassed during the following hours. Another important element is monitoring the grid. The more the grid becomes an active system, the more it becomes critical for the grid operator to have a picture of the state of operation of every node in the system. This is a problem. The state estimation has been around in power system for ages, but was never solved in distribution network. In distribution network, we have several challenges that make this problem peculiar. One is the size of the problem, because we can have several thousand of nodes that have to be solved very often. The more we increase dynamic, more often. So coming also to a discussion on getting even faster than a minute, maybe in the second range. And at the same time, we also have the problem that the information available from measurement point, in many cases, is not sufficient in a model-based solution to reach a realistic prediction, or actually any prediction at all, because you get into a deterministic type of studies in which you have to invert the metrics, and if you don't have enough input, you cannot simply solve the problem. Here is where using artificial intelligence seems to be a promising approach, because it will better support the calculation challenge and also will not require the so-called observability conditions, which relate to the number of measurement points. There will be too many to apply a classical model-based solution. So we develop algorithm for this purpose based on neural network and implemented this in real application. And currently, actually, a spin-off company from my institute is commercializing the knowledge we acquired on how to train neural networks to perform this type of calculation. And they're able to achieve very accurate results with a very limited number of sensors. So in this case, the application of machine learning to the grid behavior allows the operation, limiting the cost of installation of devices that will support the measurement point. As before, this is not just academic work. I mean, there was the beginning, but then the spin-off company had the chance, and so I asked them to provide me some slides here on determining the quality of the measurement, and you can see that the percentage error is very limited in the calculation compared with the real value. Let's say is incorrect theoretically to call about real value, but let's say value coming from measurement in different node points and going to quite large network. Here is a system with 40 substations. That means getting immediately in the 100 of variable to be predicted. Here 250 substations, a quite large network in the south of Germany that have been used for this experiment. And again, if you look at the uncertainty, we are keeping the uncertainty under the 1%, but with a very limited number of measurement in a way that would not be possible with model-based approach to perform any kind of analysis. Same here in a time domain type of comparison between the measurement points and what we are able to estimate thanks to a neural network. And again, you can see that the results are very much supporting the kind of work that the grid operator will have to do, because an accuracy 1% is definitely enough for the operation. At the end, from a power quality perspective, what we want to be sure is that we never go over the limit of plus minus 10% in the grid, so on the nominal voltage, so accuracy 1% is already a very good estimate that, let's say, grid operator in the real life practice are pretty happy with. A last but not least example that where we have been using deep learning algorithm is the problem of fault location and service restoration. Here the problem is the following. Again, we refer to the distribution grid, so the grid with very close to the customers with a huge number of nodes. And in this case, the problem is whenever we have fault situation, we need to be able to quickly understand where geographically and physically the fault is, isolate the minimum part of network to minimize the damage to the customer, and then using this information or location also to send out people and take care of the fault in, as fast as possible. So the information location plays two roles. On one end, allows you to isolate a small part of the grid, so that's the so-called service restoration, try to work around the failure. At the same time, is used to send out the crew to take care of the fault as quickly as possible. So it has a critical impact in the quality of service. And even here we have the chance to try this in a real grid situation. That's referring to a grid in which we perform our field test in Romania. What you see here on the graphic is the situation on the picture is there is a fault, basically at 6 p.m. that brings about 1,000 customers to be without power. In the old fashion, before we had this kind of algorithm available, it would take it will stay on the lower part and then finally fix the problem simply, so to speak. But that means 4 hours roughly without energy, 3 to 4 hours. Vice versa, through a sequence of reconfiguration of the network allowed by the fault location identification, and we are able to quickly bring back some customer, then other customer, then at the end, more than an hour before, the energy to everybody. But we have been estimating that this type of scenario will increase the quality of the index of reliability, which is called SAIDI, which is 10%. This maybe doesn't say much to people that are not in the field. What is maybe more interesting is that the money is saved because the penalty reduction is in the range between 20 and 30% on what the grid operator will have to pay to the what in German we call Netzagentur, so the supervisory body of the government for the quality of service. So in conclusion, the digitalization is completely transforming the option we had in grid management.
Is closed.
Future system will have higher level of flexibility.
Professor, you can continue. Professor Monti, I think we cannot hear you now. Maybe you are muted now. Can you unmute yourself again? Yes.
I don't know why I was muted. When that happened?
It happens exactly when you said the digitalization of this last slide. So we missed only a few sentences.
I don't know. I didn't touch anything. This was a self-induced operation on the computer. Yeah. I mean, my main message here is these methods are making already their way to application. At the same time, these are really first research-driven experiments. So as you mentioned at the beginning of this talk, there is a lot of space of cooperation between the fields to shape and improve what is currently done. Thank you for your attention.
And indicating just to 2 points. The first one is the uncertainty in power systems is increasing, and AI can help solving such issues. It's the second model-based solution, which provided like a solution in the past may fail or may fail very soon to solve the same issue with the increasing uncertainty in the near future. And then Professor Monti and his team started applying AI and deep learning and neural networks in solving such issue. But on the other side of this part, the trust, okay, we have a solution, let's apply it. They say, oh, how do these neural networks make their decision? Unfortunately, this is not fully understood yet, but we have a big hope with this new method or theory provided by Professor Tishby. And hopefully it's gonna bring the trust to deep learning and see the application of deep learning very soon trusted in the field of energy. And this is a good introduction to move to the second keynote speech provided by Professor Tishby from Hebrew University. You have the floor, Professor.
All right, do you hear me?
Yes.
Yeah, okay, so thank you very much again for this invitation. It's not my usual audience, and I'm going to give you a very brief outline or sketch of a theory which requires a little more than 15 minutes to explain, but I hope I can give you some sort of intuition. By the way, I turned on this subtitle of PowerPoint, which I found quite useful for international audience like this. I hope it doesn't disturb you. It's not perfect, but it's not too bad. So I'm coming from the Hebrew University of Jerusalem. I'm a physicist by training, and I spent most of my life on machine learning, even before it was called machine learning, and the connection between physics and biology in particular. So again, in this very short talk, I essentially just want to overview this framework that we call the information bottleneck theory of deep learning, which is essentially a theory of large-scale learning, and it becomes more and more relevant when we talk about very big problems, where the input, both the input and the layers and the data, of course, are sufficiently large, so that we can use asymptotic theories like statistical mechanics or information theory, which are very, very close in spirit, and that's what I've been doing for many years, since the 80s. Luckily, the problems actually became large enough, had become large enough to be relevant for this type of theory. So I'm not going to talk about everything in this outline. I was thinking about a longer talk, but I just want to give you the gist of it. So we are thinking about, we really want to understand why and how deep learning works, and the way I think about it is to think about information in the Shannon sense, information in terms of bits per second or bit rates, flow through the layers of deep neural networks. And essentially, just for to make sure that you understand my notation, I'm thinking about the input of the layer as one big random variable, like the pixels of an image, or the some section of speech, or section of other stream of information source. So this is a high dimensional random variable, all the pixels together. And I think about the label as the Y, the desired label, which is essentially part of some data given to the training algorithm. So you're all familiar with this joint distribution of patterns and labels. By the way, Y can be in principle one bit, like is it me in the picture or not, but it can also be as complicated as X itself, as in autoencoders or in other applications of neural networks, which I'm not going to discuss now. Essentially, what happens in neural networks is that X is going through a cascade of representation transformation. That's what we call representation learning. And I'm interested in only two quantities, essentially: how much information each one of those hidden layers maintain about the input per pattern, on average per pattern, and how much of this information is used, is valuable or useful for predicting the label. So that's a very basic question that I can measure with this notion of mutual information, which essentially is the cross entropy between the joint distribution of the input and patterns and the product of the marginals. Or you can think about it as the amount of uncertainty removed about the pattern when I know the label, the entropy difference. What is interesting about the mutual information, or at least it's good to know that when you go through a Markov chain of representations, just like in my layers of the neural network, I can only lose information. So information can only get lost when you process information in a Markov chain like this. And this is called data processing inequality, and I'm not going to talk much more about it now. When you apply it to neural networks, there is a chain of inequalities. The mutual information about X is going down along the layers, and the mutual information about the desired label is also going down. And I'm very much interested, as I said, I'm going to skip some theoretical details here. I'm very much interested to characterize this by essentially two quantities. Each layer is characterized by an encoder, which is a map from the input to the layer, which is in general a stochastic function. So I think about it as a conditional probability distribution. It can be also, of course, it is a deterministic function in most applications, but when you talk about very large inputs, this distinction is not so important. So it's easier to think about it as a noisy version of, so the layer is some stochastic function of the input, and that's what I call the encoder of the layer. And the decoder of the layer is the map from the layer to the desired label. And essentially this encoder-decoder picture, which is very common now in analyzing neural networks, is what makes this related and useful for using information theory, because although it's not a communication problem as in information theory, the connection between the encoder and the decoder is precisely the heart of the communication problem. The map from the source to the channel and from the channel to the output of the channel are precisely related to this encoder-decoder problem. And my claim is that for typical large problems, and that's something we need to explain, everything is characterized, everything in terms of sample complexity and accuracy, error, generalization error, are characterized by these two quantities: the mutual information of the encoder and the mutual information of the decoder. Why is that? I don't have the time to explain now, but you can find it in various papers now. And essentially, I'm also interested, especially in this talk and recently, in what we call local learning, only in the map between three consecutive layers, the layer Ti or Tj minus 1, the map from it to the next layer, and from this layer to the next layer. So, and I argue that when we actually optimize the network, the map, this local bottleneck problem is also optimized. So as if this was the input and this was the output, and then the middle layer is optimized itself such that the local encoder and the local decoder satisfy the condition that I'm going to describe now. So essentially, when we talk about a large neural network, the interesting picture is this plan of mutual information of the encoder versus mutual information of the decoder. That's what I call the information plan or the info plan. And the interesting story is that when you actually look at the training of the layers. So what you see here, every one of those points is a single layer in an experiment with 5, in this case, it's small 5-layer neural network, and we did it 100 times with randomized initial conditions and randomized samples. And the interesting story I want you to take home is that when you actually train this network, you see these very interesting trajectories in this plan, and all the different layers, although have completely different weights, seem to follow a very similar trajectory, which eventually look like that. I mean, so all the layers start from the last layer, which is really what I care about, how well it predicts the input, has very low information about the label at the beginning, but during this training, it comes up first to a point which, in a very fast drift phase, which happens essentially everywhere in this story from A to C. So all the layers come up because of data processing inequality. Information can only go down. So they all move to this middle place first very quickly. And this is what I call the drift phase, which essentially happens when the gradients of the training are very clean and there's little noise, little fluctuations from mini-batch to mini-batch in the gradient. This is fitting the data. And then there is this very case, which we were the first to point out, that from C, which is most of the training essentially, will happen between C and E here, where the last hidden layer eventually get to a point which has essentially the same amount of, or the minimal amount of information, which is 1 bit in this case, about the input, and the same maximum, about 1 bit about the output, which means that the last layer serves as what we call minimal sufficient statistic, or essentially it really forgets all the information about the input except the 1 bit that I really care about. But what is really interesting is that in this plan, we see what all the other layers are doing, and that's a unique feature of this type of visualization that you don't see in most theoretical approaches to deep learning today, which really don't care much about what happens in the different layers. But you see that all the hidden layers essentially follow a very similar trajectory in this plan. They start from this what we call the privacy funnel, the minimal information that you must contain about the label at a given compression of the input. So this is also an interesting line, which I don't want to just give you this insight that there's something interesting about this line. But then they all move to this more or less straight line here. And from that point, most of the generalization is gained by essentially compressing the representation, which means losing information about the input. And that's a very interesting insight that we are trying to explain both theoretically and numerically with many different experiments. What I can tell you now that the same type of picture is observed for very large problems and including CFAR and MNIST and essentially all the benchmarks used in machine learning today. But of course it's very difficult to measure information, so we use all sorts of variational estimates, and you can read about it when you look at the variational information bottleneck method, for example. There are various ways of estimating information, but if you do it correctly, this is the kind of picture you see with almost all types of neural networks, with all kind of nonlinearity, whether they are linear or sigmoidal, I mean saturated nonlinearities, or things like ReLU, which we are using all the time, rectified linear networks. Essentially, you get this compression phase in all the cases unless you don't measure information correctly. And the interesting question I'm trying to figure it out now, first of all, what happens when I don't have enough data? So that's this picture. Essentially, if you don't have enough data, so again, this is the same traces in the information plan. This is with a lot of data, with 80% of the samples in this case, and you see that this compression phase is essentially not losing almost any information about the label. So this is very good generalization, because there's essentially good prediction of the label. Then mutual information about the label is abound on the generalization error. So but when you don't have enough data, like here, you have this essentially effect of overfitting. You see that the first phase, the fitting phase, is essentially identical to what happens with large data, but the compression phase misses this high information gain and essentially go down. So here, something like early stopping or all sorts of regularization can help you when you don't have enough data. What I actually argue is that we have a good theory that can tell you exactly what are these lines in this information plan to which those layers converge to. And this theory is what we call the information bottleneck. Again, I'm skipping some details, So essentially, you can calculate analytically or numerically this bound. It's very highly exaggerated here, just to make things clearer. This black line here is the compression, a given information about the input, and at the same time, and this can be solved by essentially just solving this theoretical variational problem, minimize the information of the encoder subject to some constraint on the information of the decoder, and this beta is a Lagrange multiplier here, which essentially is just 1 over the slope of this curve, which is very much like a rate distortion function for those who know what it is. What is really interesting is that the theory is really telling us the connection between the encoder and the decoder, which is summarized by these 3 equations. So essentially, you see that the optimal encoder is exponential in the KL divergence in the actual decoder, and the best decoder done from the data. This is not something which is usually accessible to you, but the connection between, and the optimal decoder, of course, is just the base optimal, which is just this very simple average of the encoder over all the data. So this is, again, and this is actually easy to perform in practice. And this one is what the theory predicts that the encoder is going to be. So what is nice about it, that if you are right, and essentially the stochastic optimization is taking you to this limit, we actually have an analytic connection, a mathematical connection, which can explain many of the features of deep learning, in particular why they fit so well different types of data, what type of data the whole thing works for, and many other issues, essentially by using those theoretical prediction or theoretical connections between the encoder and the decoder. Notice, by the way, that in high dimension, these things are very hard to solve, because if x is megapixels and x hat are also millions of variables, this joint distribution are not directly accessible. And we need to use all sorts of numerical and analytical tricks to actually estimate or approximate these self-consistent equations in very high dimension. What is really also interesting to notice that if you don't have enough data, so the true information when with finite samples, it drops down significantly if you're trying to use over detailed representations. So there is some sort of an optimum here, which tells you that your last layer should be somewhere here, which is the maximum achievable information about the label at a given level of representation compression. So even if your networks are something like ResNets or RevNets, which essentially don't lose information, the decoder cannot use more information than this red line. And that's why compression, or at least effective compression, is essentially essential for good generalization. And that's something which is highly debatable in the literature in the last few years, but I still stand behind this very basic bound. So there's some sort of a generalization bound which is associated with the compression, and without the compression you don't generalize well, at least not effectively. I mean, you can keep a lot of unnecessary information if you want, but you don't really use them in the decoder. Now, so this is the gist of the theory, and we actually see that in real neural networks, the final location of the layers lie very close to this theoretical limit with some statistical scatter. So we can actually assume that the layers of deep learning really satisfy this self-consistent equation. And that's a very big story in terms of understanding what the neural networks are doing. Let me just give you one interesting application, because I have to finish. Essentially, when you increase the number of layers, the time to converge to this optimal bound, if it is achievable at all, if the network is sufficiently expressive to actually get there, is going actually down significantly when you increase the number of layers. So here again, the color represents the number of epochs or number of training updates, and you see that with more layers, we actually converge faster. And that's actually, again, we see it in real neural networks, and we see it in practice. Let me just show you how it looks in some practical applications. I mean, essentially, this feature, I don't have it here. The number of the time that it goes to converge goes down like a power law a negative power law of the number of layers. So more layers converge faster up to a point, and this point is essentially the optimal number of layers for this problem. It's a problem-dependent bound, it's a problem-dependent property, but this is the beginning of some theory of design principles for how to design your best architecture for a given problem. Now, I'm essentially out of time, but I just want to mention something new. So essentially, we can actually solve this local encoder-decoder problem by taking the same encoder-decoder equation and localize them. And the way we do it is just sketched again in this slide. We take the log of the encoder, the variation of the log of the encoder, and see how it's affected by a variation of the log of the decoder. And this gets us into something which I call the local information bottleneck equation, which is really very interesting. First of all, it's much more efficient to solve, and I don't need to use backpropagation or derivatives or backpropagate using the chain rule, the derivatives through the network. And this type of things are now becoming of large interest in many different places. How to train neural networks without using this relatively complicated and expensive process of pushing the derivatives through the network, and you can actually localize and distribute it in a distributed way, optimize 3 consecutive layers everywhere. This is going to be even more important when you think about biology or about things in the brain, because there everything has to be local due to the constraint of biology. And I just want to summarize. So essentially, the main message is that for large neural networks, only 2 numbers, the encoder mutual information and the decoder of the mutual information of the encoder and mutual information of the decoder really govern the picture asymptotically for typical behavior. It's not a worst case behavior, it's a typical behavior of the problem. And this allows us to get a very interesting insight about the structure of the layers, where do they converge to, what each one of them is represented, and then again we can localize the learning without losing essentially anything about the performance by essentially optimizing each layer between the previous and the next layer in the network. And this is what I call the local information bottleneck. And of course, there are many other different issues which I don't have time to get into. So I hope you at least try to find some longer talks on YouTube or look for our papers, which are most of them are on the archive or available. And not much of what I told you today is actually published. All right, thank you very much.
Oh yeah, thank you very, very much, Professor Tishby, for a very short and like rich talk. So you have the participants today have a lot to follow up on to learn about mutual information, and how to measure mutual information is a big thing. But yeah, very interesting theory, and brought up a lot of arguments in the community, in the AI and deep learning community, big discussions in the last 2 years. And of course, also you have received a lot of critiques, and I have read all of your replies. But thank you very much for this work, and it's gonna make a change, difference, hopefully soon. And the first recognition is the award you have received for this work, 2019. Now we have we are going to open 5 more minutes for questions for the 2 speakers, and you can just raise your hand, and I'm going to give you the word to ask. Just you say your name, to whom your question, and then ask your question, please.
Hello. I'm not sure I see the video here is very strange. I don't see other people.
Who's talking now?
Well, this is me. This is Naftali Tishby.
Oh yeah,
I'm still looking for questions, but I don't know where to look for them.
Yeah, I think we're gonna receive 4 questions, and they should simply talk. Like whoever wants to talk, raise your hand with the tool, and then start talking, please. Yes, first question, and then you can from from Soroki. Yeah, but unmute yourself and start talking.
Hello, yeah, I am Amin Shokri from Kasra Institute of Technology, KIT. So I have a question from Professor Monti. So if I remember, that was a slide 8 or 9. Is it possible that Professor Monti share the screen?
Yeah, let me try.
10, I'll 10 mine, yeah, 10 of mine. Now everything is free for sharing.
Wait a second, because I have to leave the full screen or we'll get in the same problem as before.
Yeah.
Yeah, maybe you can start the question. Well,
just like you can just
the question. I remember that was about flexibility and question that you said that in the corresponding project you have 40 hours actually like a day ahead market for that, but when we talk about flexibility, they are very fast services, so I didn't get the point. Maybe I misunderstood, because of that I asked why 40 hours before.
Yeah, no, you understand correctly. It's a 40 hours. It depends on what kind of flexibility you're talking. This is not a local market of flexibility for the DSO internally. This is a market related to the interface between TSO and DSO. And that comes from the Swedish regulation, so you don't find anything similar as a one-to-one in Germany. But as I mentioned, there is this regulation that defines the amount of power that can be exchanged between TSO and DSO. And the logic says that anytime they go over this limit, they have to pay an amount to the TSO. So the DSO wants to know 40 hours in advance if they need to access flexibility to avoid to violate this limit.
Okay, so it is flexibility market, or it is just like a reserve market here then? Because when normally flexibility and reserve could be different markets, and then flexibility is just something very fast provided, so it is not
necessary. I think different flexibility market, and actually this is the direction I'm currently just starting a new European project that will put together all the flexibility market together. There are several markets of flexibility that have been envisioned. This is regarding the interaction between TSO and DSO, and it's not a fast market. But you're right, there are also one with fast market.
So it is just
time. We don't follow up question, please, because the time is so limited.
Okay.
So thank you for the question, and the next question from.
Thank you. Thanks for your answer and explanation.
Theo Evans, please unmute yourself and ask.
Hello, can you hear me?
Yes.
Yep.
Hi, this is Theo Evans from the Technische Berlin. I have a question for Professor Tishby as to where does the element of biological plausibility come into informational bottleneck theory?
Okay, so I said it really very quickly. But what I said is that when the network is converged, all the layers sit on this information bottleneck curve, which means that every layer is an optimal bottleneck between the layer before it and the layer after it. So in some sense, it is forming what in information theory we call a successively refinable code. So this local optimality, it's like, you know, a Bellman equation in control or something like this. I mean, essentially, I can solve now this optimality problem locally using only local derivatives. And that's exactly getting rid of the need to use chain rules of derivatives like backpropagation or other techniques. So essentially, we can localize the learning rule when you get close enough to the optimal bound. And essentially, the mathematics is just based on the stability analysis of the bottleneck equations. There is another related story which tells you where are those layers converge to in terms of the structure of the problem, but that's something I didn't have time to discuss. So the plausibility, biological plausibility here is in the localized gradients. I'm not using chain rules of derivatives and don't need something like backpropagation.
Do we have more questions? We have. Okay, I No more question. I have one question to Professor Tishby about the Relo. So a lot of discussion brought to criticizing information bottleneck theory because they say the compression did not show in the case of Relo activation function. And then I also saw your replies, but they still argue against that. And I just wondering about whether this do you see the maybe it's just the way they measure the mutual information, so they measure it not in the right way, like wrongly, or do you see the unbounded feature of the activation has an impact on this?
Yeah, so you're referring to the by now famous paper of Andrew Sachs and others from Harvard at the time.
Yes.
We immediately, even before we published our paper, responded that this compression depends on the way you measure information. In particular, ReLUs, the binning techniques that we were using in the first paper works well for saturated nonlinearities like sigmoids, but not for something which is unbounded like ReLUs. And so they wrote a very quick paper, which they refined later. The main issue, I don't want to get into these technical details, but information is a very tricky quantity. If you have infinite resolution, information can easily go to infinity. And actually, if you don't lose information because of some sort of noise or discretization or quantization of your variables, then in principle, all the maps from the input to every one of the layer is a one-to-one map, and there is no loss of information. So the problem is that in order to define information properly, you must take into account the actual precision or the actual quantization of your data. And this is theoretically justifiable, ever since Kolmogorov started to think about information in the 30s, in the 40s and 50s. So essentially, this is not something new, but when you talk about continuous functions which are in principle one-to-one, then of course there is no loss of information and you don't see any compression. But once you add some small noise to the problem, either by quantization or by precision or by some intrinsic noise in your network or intrinsic noise in your data, then the whole thing immediately collapses to the picture I described. And this is and of course there is also a very big issue about the role of regularization and boundedness of the units. So what I'm saying is that I still stand behind my story. It has to be modified and stated much more carefully. I didn't have time to do it today, but I think the argument is still open to a large extent, but more and more people see this compression even with variational methods and other techniques of estimating information, which are much more practical. The issue with information is not whether there is compression or not, but how do you estimate it for large problems, because density estimation and joint probabilities in very high dimension are very ill-posed and ill-defined. So there is needed to quantize and to regularize the problem just because you need some reliable estimate of information. So it's a long story. I'm sorry I cannot.
I got it. I just want to know whether the unbounded Relo, so it's just the measure of information, or does the unbounded activation of Relo play a role in this game?
Yes, so even for unbounded ReLUs, there is some sort of regularization that keeps the weight finite. Otherwise, they can grow forever. But if you don't regularize it, then you have to think about the actual distribution of possible weights and redefine the problem appropriately. It can be done. Can be done. I don't have time to
that. Thank you very much. Thank you very much for that. And you can always post your questions on the chat room, and we will look at them at the end. We are going to move now to the last talk from Christian from TU Berlin. Can you please, Christian? Can you please unmute yourself and start the conversation, like your talk on explainable AI?
So let me just see if I can share the right screen here. Can you all see that?
Yes. Okay. So this is explainable AI in practice, more in practice, not in theory, as explainable AI. Yeah, it's becoming more and more important now in the field of energy as well as in many other fields. So Christian, please, you have the floor.
Okay, yeah, thank you. So good afternoon. Today I want to talk about perspectives on explainable AI. And when I say AI, I mean it in really this fuzzy way. So complex systems and not just machine learned models, but the whole application. And I want to focus the explainable AI topic on critical domains. So I think it's of real importance to have explainability in AI systems where that affect really critical domains. So the motivation for explainable AI for me and for this talk is basically the desire to build safe and trustworthy systems. And when we talk about AI, we often hear this term black box. So it's a nice picture, but if we take a closer look into what this black box actually is, we see that it basically depends a lot on the perspectives that we have on the whole AI system. So what I mean by that is, if I'm an end user and I'm affected by an AI system, for example, because I'm browsing the internet and I get commercials displayed. For me, the black box in that situation is much more than just the AI system itself, but the black parts that I can't see are even some of the inputs, for example, a profile that is being collected about me, and also about the output. So maybe there is additional information output by the system that I don't have access to. So it's completely hidden by me. The other very different perspective is the one from of the developer of the AI system. So from a developer's point of view, that black box is actually not really a black box. I can open it up. I can investigate the source code. I can track the variables. So everything is open to me. But what actually causes the black box is the sheer complexity of the models inside, or the sheer number of different information that I have to keep in mind at the very same time to get a grasp of what the system is actually doing. But why is this a problem? I mean, end users already use intransparent systems all the time, and they learn by historical examples to trust them. I mean, people use cars, although they don't understand every single aspect of the different highly complex systems that are being put into a car. And we also trust computers, so the CPU and other components to just run, because we have experienced that they work and for a long time. So yeah, we just trust them. And we even trust some AI systems today. So, I mean, everyone uses navigation systems, GPS, maps, traffic information, all put together, an AI system that leads our way through the world. We trust it when we use a search machine. We trust it to some degree, hopefully, in translation, although sometimes this trust is not really justified. We use it for risk estimation, scheduling, and whenever we experience that it works for quite a long time, we build up trust. So trust helps us basically to deal with this complexity of the world. But especially in long-term systems that we use all a long time, and with systems where a failure has a large impact, maybe we would like to have a safety net, because this trust can sometimes be misleading. And there's also another thing. So if we have an AI system and there is a possibility that it can be used in a very wrong way. So as an example here, we have an upscaling model that takes a low resolution image and it fantasizes a higher resolution image from it. If you take this image and, for example, apply it on security cameras and then you are looking for people that look like the right example here, you might find wrong people, and basically this is the outcome from using the system in a wrong way. You do not understand in this sense what you actually get from this system. And yeah, but understanding the underlying mechanisms doesn't only help us to build better systems, or no, it doesn't help us to understand what we get, but it also can help us to build better systems in the future, and and it can help us to judge when not to trust a system. So here we know birds, build airplanes that were looking like birds, didn't go well. Then we did understand why birds can fly, and we were able to build better birds. And we can, even by understanding the underlying principles, we can build stuff that on the first look doesn't look like it should fly, but we have the trust and know, okay, by understanding the principles, we can derive, okay, we can also trust this thing, although it looks weird and we don't have historical examples of it. So here, explainable AI basically can provide the safety net and can help to bring more transparency in systems. And it comes also with a couple of more features that it can provide. I think one of the most important ones currently in politics is this fairness aspect from the GDPR. So to help discover bias in learned models, to make sure that the system is not discriminating in an unfair way, for example, but also some other parts. And this basically is powered by the exploding number of research papers on explainable AI in the recent years. And it provided us with a couple of tools that you can use to build practical AI systems. So just again, to recap, so explainable AI is not just about explaining the machine learning models, it's also about explaining the whole complex systems to the different stakeholders. So there are many more, but here I've just three. So the developer perspective, the perspective of the regulators, and the users. And the most extreme ones are the developers and the users ones. And regulators are probably interested in both perspectives at the same time. So within an AI system, explanations can come from very different stages. So we see here a user might, for a better transparency, a user might be better informed about the whole input information that is put into the system. And the user is also interested in seeing the whole output of a system, so whether or not he is being tracked or something like that. But for some users, it's often already a real benefit if you can see intermediate conclusions. So if we have a complex AI system that is using a lot of machine learning models, segregation models, classification models, and so on, it is sometimes increasing the trust in the system if you just show the user also what are the intermediate steps to coming to a conclusion. It helps the user to better judge if the system, the whole AI system, is on track. But of course, most of the existing approaches focus on explaining the machine learned models inside of an AI system. And we have here different levels of explanations. So we have individual predictions, also called local explanations. They are typically explanations of when a model is getting one example, one instance, and predicts something, and it explains why this prediction happens in this way or on which features. Then we have an explanation of the model behavior. That's a global explanation, not focusing on one specific instance, but trying to explain the whole behavior of the model. not really a very different category, but also familiar to that are learned representations. These are explanations that try to show what the model learned, for example, by visualizing the latent space inside of a neural network or specific neurons inside of a neural network. And then the fourth level is representative training examples. So, for example, if the stuff that the model has learned, the concepts can be derived to specific examples in the training set that are really representative for or very influential in the training process. Then another viewpoint on this is point of view is types and formats of explanations. So we have explanations by simplification. So often by approximating the highly nonlinear models by simpler models on a local scale, for example, that then help us to understand the interconnection between the input and the output. We have feature relevance, so to say to investigate or to show which are the most important features that lead to a specific classification, for example. And then more on the format side, we have visual and textual explanations. So visual, we will see a couple of these later, are explanations that, for example, on a picture, highlight the areas that are most influential, and textual explanations are the ones that provide text, natural text that explain the model or the AI system in a more natural way. There are nowadays a lot of explainability approaches. This is maybe a bit too much, but you're free to, of course, look it up. I've made this a bit simpler by taking only the highest levels here. So on the highest level, you can say XAI is you can divide it into inherently interpretable models. So models that are so simple that you can that you can interpret them on their own, and post hoc interpretable models that are too complex for that, and where you need to find another way to provide the explanation. So for the inherently interpretable models, some examples are, for example, linear regression, decision trees, Bayesian models that are the ones where and decision trees, so simple decision trees, where you can manually look up what's going on. And for the post hoc models, we can say we have model-specific ones and we have model-agnostic ones. So for the model-specific ones, there are lots of different explanation approaches here, and I just picked a couple of them here. I can't possibly go over all of them, and all these that I picked are basically for images, image classification systems. So the first one is a layer-wise relevance propagation. It's an approach that is model-specific, but can be quite simply integrated for neural networks, especially convolutional neural networks, but also other types. And the idea is here, if you have a classification, you base it by backpropagating the class labels back to the input image to find which are the most influential pixels here. It's a local per instance explanation in this case. But the good thing is here that it's not too expensive to do this. The second way to explain something is saliency maps here. This is quite expensive because it's model agnostic, meaning that it only takes the input and the output and access to the model in the way that it samples random vectors from the instance that you want to investigate, and then looks at the output and how much it changes. And because of the sampling, it's of course quite expensive, and denoising techniques are required to get a better picture here. And the problem is for all of these approaches that you need some kind of machine learning background to interpret what you see. This is the last approach that I want to present. That's LIME, local interpretable model agnostic explanations. And the basic idea is here to approximate, do a local approximation of the model on one instance. So on the right hand side, you see here on the top that we train a linear classifier on this SVM learned model, and it helps us on this very local area to understand why something is classified as this and this, and what are the related pixels. So now coming to an example where everything is put together. So I'm coming currently from the background of medical systems, and here we can see an example how everything can be put together to create a user interface that is using saliency maps, for example, or textual explanations, information that is coming from inside of the XAI process or the AI process, that helps the user to get a better understanding and control of the whole system, and helps him to justify if the final classification or guess that the system is providing him is justified. So as a conclusion and future work on explanation methods, so there are a lot of open topics right now. So we have already a couple of systems and approaches, but what really is missing currently are objective explanation measures. So ways to measure how well an explanation is. And it's quite difficult to find objective measures because in the end, it's a communication thing. It's something you need to explain it to a human, and explaining it to a human is difficult to express in a formal way. So this is something where empirical quality measures are required, which are often difficult because of the high cost that come with them. Another really open topic is the problem of the current explanations being on a very abstract level. I mean, saliency maps are quite difficult to interpret, especially for end users that do not know much about machine learning, about statistics, and it's easily to get it wrong. So that brings us back to this picture of the low resolution to high resolution system. They can be interpreted in a wrong way, and this can be dangerous. So it's better to have some ways of explaining AI systems that are closer to humans, so including the human factors. And this actually bridges or goes into the direction of human interface research, which is quite unfamiliar for machine learning researchers. But somehow this needs to be connected together. And the last point is expanding explanations beyond the visual ones. So finding additional ways to provide explanations to communicate with the user. And on the last page, I want to give a recommendation. So if you are further interested in explainable AI, I can highly recommend this book from Samek et al., giving a really good overview about the whole current state of the art. And I want to give a thank out. I want to thank the Bundesministerium für Wirtschaft und Energie that is funding the Empire project I'm currently working in. And this concludes my talk.
Thank you very much, Christian, for the interesting talk. Then we see now another perspective of explainable AI more in practice and the end user. So maybe the end user, like with the time, can't trust AI applications, but from my experience and communication with big firms, they need explanation usually. So the end user can trust the big corporates take take time to trust. That's why, and for some application explainable AI, to understand and need to improve it. For example, what Professor Tishby today suggested, that it could change the whole story instead of using a stochastic gradient descent to train, which is the biggest thing in the training now. It could be much easier if we really understand the inner dynamics of of neural networks. This takes us to the next step of our unfortunately we're not going to take questions on this talk, but please just post your question on the chat. I will make sure to forward these questions to the speakers and get answers and get to you back. This takes us to the next step in our event, which is the workshop. So the outcome is going to be a set of slides. We are going to edit this slide, complement it with publication, and send it to everyone, so that anyone wants to start researching in Apply AI Energy takes this slide and having as a start point. As a PhD student, it was a struggle at the beginning to have the first starting point to work on. I'm going to hand over to our teammate Louisa to show you the organizational aspect of our workshop and how are we going to take this. Yeah, please, Louisa, you have the floor. Unmute yourself.
Thank you. Yeah. Yeah, a warm thank you from my side again for the great input. I will share my screen. Right, so we have planned a small workshop session right now. It's going to be short in time, so fast-paced. It's basically going to be mainly brainstorming, like Mahmoud was already saying. It's supposed to narrow the gap between AI and energy. So we hopefully create in the end a lookup table for possible applications of AI solutions within the energy sector. Just in general, for brainstorming, we want to avoid judgment. We in general encourage wild ideas, so just get everything out you want to share, and also we want to try to encourage you to build on ideas of others. The setup is going to be roundabout groups of round about 10 people. Hopefully, we're not that many anymore, but we will have a time frame of 20 minutes approximately, and we will then come back into the main room. So for the brainstorming sessions, we are going to be in smaller groups. Yeah, like I just mentioned, we come back to the main room and have around about 3 minutes to share our results. The procedure is going to be as followed. We will have a fast brainstorming session where we collect all ideas that come on mind. They are going to be shared within a chat, and the moderators, so we have one moderator per group, is going to collect them on sticky notes, and after that we'll have 5 minutes to cluster the ideas and yeah, find common ground or group the ideas, and in the end we again have time to build on top of the ideas of each other. Yeah, so far that's from my side. Have fun, and the next step would be following the link we sent via email, and we'll also post it in the chat right now. Again, minor changes. The people who were in the group Naturals are going to join the Elite, and Avengers are going to join the group Arrow. Yes, thank you from my side.